Now I'm going to use the notion of multiplicative functions. I'm going to use it in 3 or 4 distinct ways. I'm gonna prove something. Well, I'm gonna sort of half prove it. I won't give an entirely rigorous proof, but I'll give a heuristic proof. See how it goes. If f of n is multiplicative, and if f of n, capital F of n, equals sigma over d divides n of little f of d, then big F of n is multiplicative. Is multiplicative. Well, that's nice. That's a nice little result, that is. And so we can see now that the multiplicative, the definition of being multiplicative is quite nice, because you've got this beautiful little theorem here. I don't think it's named after anybody, at least if it is, I don't know. So let's prove that. Well, let's just. I need to start with something. I need a thing called a lemma. If I've got two numbers, let's say a and b, which are relatively prime, and I've got d divides ab, then d equals d1 times d2, where d1 divides a and d2 divides b. This is quite straightforward. If I look at the prime factorisation of a, which is p1 to the alpha 1 through to pr to the alpha r, and b equals p... Oh no, it's not. It's haha. It can't have a p1 in it because they're co-prime. So it's got to be q1 to the beta 1 all the way through to qs to the beta s. You can see that if we need a divisor of this product here, it's going to have some p's in it and some q's in it, and so it's got this feature here. So I'm just going to start with that. This is actually, this lemma here, if d divides ab, then d equals the product of a divisor of a and a divisor of b. It's sort of not misleading, it's kind of deceptive. It's deceptively powerful, that little lemma there. It crops up quite a lot, and if you get your brain around it, and once you recognise what's going on, it can be very, very helpful. It's deceptively deep, this theorem. I know it's not difficult to prove at all, but it's not straightforward. Anyway, let's have a look at this. So what am I trying to do? I've got f of n equals the sum over d divides n of a little f of d, and I want to prove that f of n is multiplicative. What I want to do is, I want you to observe while I'm talking that I've got this sort of thing I want to prove, and I'll just see, to prove that it's multiplicative, well, let's just write out the definition of multiplicative. So we've got f of mn equals, so we want to show, that equals f of n, f of m. You see, that's not quite right, but this is only true when m and n are co-prime. So let's start that again. Let's cribble that out and start again. So I want to show that mn equals 1. If they're co-prime, then capital F of mn, that's a funny m, equals capital F of m, capital F of n. Okay, well, let's just have a look at it. Let's have a look at f of mn. This is capital F, and that equals, by definition, the sum over d divides mn of little f of d. By definition, this is the relationship between the lowercase f and the uppercase f here. All right, well, let's have a look at that then. So that's going to be equal, because d divides the product, d itself must be equal, d must equal d1 times d2, where d1 is the divisor of m and d2 is the divisor of n. So this thing here equals the sum over d1 divides n and d2 divides m of little f of d1 times d2. So we've split apart this d here into two bits. d1 dividing n. Oh, I've got it the wrong way around. Never mind. Okay, well, let's have a think about this. Well, I know, what am I using? In that Polya sheet, the Polya how to solve it sheet, the upper sheet, which I still haven't printed yet, but in the upper sheet, it says, have you used all the data? Have you used all the data? That's one of the questions it asks you. And we haven't, because so far we haven't used the fact that little f of n, here it is multiplicative. We haven't used that fact, so let's use that. Now, you'll remember the definition of multiplicative function, and also d1 and d2 are relatively prime. I'll write that down. d1, d2 equals 1. They haven't got a common factor. So this thing here equals sigma over d1 divides n, d2 divides m, of f of d1, d2, which is by definition f of d1, or by definition of multiplicative function, f of d1, d2. So f of mn equals that thing there. By the definition, by the definition of f of n being multiplicative. Okay, so there you go. Well, we're almost there. So let's just have a look at this. Well, what is this? This is the sum of a d1 divides n, d2 divides n, of f d1, d2. So I can write it out in a somewhat slightly different form. Sigma over d1 divides n, sigma over d2 divides m, of f of d1, f of d2. Actually, I'm going to write it down in a slightly different way. I'm going to scribble that 1 out there and scribble that 2 out there. I'm going to put that, which way around do I want to do it? I want that 2, I want that to be a 1 and that a 2. Is that what I had before? Anyway. And then what I'm going to do is I'm going to observe that as far as this summation is concerned here, as far as that summation is concerned, that summation is summing over d2. So that is just a constant. Okay? So it's sigma d1 divides n, f of d1, times, put brackets there, sigma d2 divides m, f of d2, equals sigma d1 divides n, f of d1, put brackets back in, times f of m. See that? This thing here is by definition capital F of m. There it is, and I'm just going to write it down, which is a constant. There's no d2 in that, there's no d1 in that either. So I can take this, that's just, as far as this summation here is concerned, as far as the summation over d1 is concerned, that's just a constant. So I can just take that out, f of m times sigma, and you can see where this is going, d1 divides n, f of d1, and of course this thing here is just f of m times capital F of n. So let's just go through that whole sequence of reasoning here. We wanted to show that capital F, this thing here, we wanted to show that capital F of mn was equal, well, up here, capital F of mn was equal to f of m times f of n. And we've gone through all this process, equals this, we've turned it inside out, we've used this peculiar result here about factors of products if they're relatively coprime. It's a very tight little piece of reasoning, this. So let me just say, I'm going to say that again. If, I'm going to pinch in, if f is multiplicative, and if capital F of n equals sigma d divides n f of d, then big F of n is also multiplicative. Wow. I'm going to give you a couple of examples in the following screencasts. But for now, I just want to sit there and think about this. This is a wonderful little thing. We've got this very, very clever, neat construction. It saves. There's a lot of steps in this proof here. There's a lot of steps. We've used properties of divisors. We've used the coprimeness of M and N. We've used the definition of multiplicativeness. This is, and we've used summations and changing the order. We've used lots and lots of features about numbers to get to this rather fantastic result. And we're going to use it over and over and over again to solve Olympiad questions. So I'm going to stop there.